In this third part of our EMG module, I'm going to provide start with an overview of the physiological signals involved in the construction of an EMG signal, and then we'll conduct a basic review of how we can quantify and actually put some numbers to the EMG signal as a reflection of what's happening with the muscle in question. And so what we see here on this graph here what we see are action potentials recorded from the surface or the indwelling electrodes. So in this particular case, we're looking at a double electrode configuration over the biceps brachii muscle while a person is performing a contraction. And we know that in order to perform that contraction, that person's central nervous system has to activate a motor unit. And so in this particular example, here we have one particular motor unit that will produce an electrical signal from the activated muscle fibers that will have this type of shape. Notice that if you recall the action potential from a single cell in a previous course, it does not have this shape. But this is the resulting shape from a dual electrode recording. So here we see a motor unit. It discharges an action potential, then another one, and then you'll see each of the action potentials generated from the activation of this one motor unit will have the same basic shape every time. But what we see here, as the contraction continues, we see that the frequency of activation starts to increase. So this motor unit, it starts activating at this particular rate, and because these action potentials are appearing closer in time, the frequency of activation starts to increase. Now what we see here is the activation of another motor unit simultaneously with this motor unit, but this motor unit here, because it's innervating different muscle fibers that have slightly different characteristics in the membranes, will generate an action potential that has a very similar shape, but there are some unique differences with it with respect to the wavelength of this action potential. So here we see with these motor unit over these muscle fibers, it's a slightly longer action potential that's recorded. It's not discharging at the same rate, but we also see that because they appear closer in time, that the activation of this motor unit starts to increase in terms of its frequency. Here we have a third motor unit, which seems to again have a very oddly shaped type of action potential, and part of this might be a result of where these action potentials are being recorded with respect to the surface electrodes. So in this case they appear to be inverted, but nevertheless when we examine the overall EMG activity, all these will eventually add up. But we see this motor unit, it doesn't seem to change very much in terms of how many times it discharges over the same period of time. The fourth motor unit, here we see a much faster discharge of the action potential, but then it discharges almost right away, and again and again and again, but now we start to see them spread out a little bit. So we would say with this fourth motor unit, the action potentials are starting to decrease in terms of its frequency, and this is going to be something important when it comes to using the EMG to examine muscle fatigue, as we'll see in part 4 of this module. We have a fifth motor unit and a sixth motor unit, and when it comes to constructing the overall signal, so if you record an EMG signal using this configuration, this at the very bottom is what the computer will produce, and this signal here is the mathematical, algebraic, or arithmetic summation vertically of all of these action potentials in time. So here we see a very clear, with the first motor unit, we see a very clear, distinctive set of action potentials, but when you start to add up all the action potentials in time across all of the activated motor units, it gives off a very asymmetrical, complex looking type of waveform that we know to be the EMG. So as we move vertically, the addition of more motor unit action potentials is reflective of the physiological process called motor unit recruitment. So motor unit recruitment refers to the additional activation of new motor units that have not been previously activated, which will contribute to an increase in force output, but will also contribute to an increase in the overall EMG activity. As we move horizontally, what we see here, so in time, so horizontally we're moving in time, that is referred to as rate coding. And rate coding refers to a change in frequency of the activated motor units during a contraction. So with the first motor unit, we see an increase in the activation frequency of motor unit 1. With motor unit 4, we see, as time progresses, an actual decrease in the frequency, how many times it's generating an action potential in the same period of time. So once we produce the overall EMG and record the EMG signal, to begin to use it to examine things such as the magnitude of a muscle contraction, whether a muscle is activated more than another muscle, so on and so forth, we have to start quantifying that signal. And the simplest, most common step that's used is something called full wave rectification. And so on the left-hand side here you see a typical what's called a raw EMG signal, and we have a deflection. We have a number of positive values. We have a number of negative values, and full wave rectification is a mathematical process where every single collected data point is converted to its absolute value. Because if we add up all the positives, all the negatives on the raw EMG signal, it will sum to 0, suggesting that there's no EMG, but we know that that's actually not true. So mathematically, what we do by converting to the absolute value, all the data points will not equal 0. The raw signal, the positives will balance out the negatives and will give an overall value of 0, which will not allow us to the process of quantifying the EMG signal. So here we see a raw signal, full wave rectification. We're moving from this signal to the right, which transforms our raw signal to the rectified signal, which now every single collected data point appears as a positive value. All the positive values remain as positive values. All the negative values will then essentially be flipped onto the positive side of this graph. Now that we have all these positive only values, we can now perform various mathematical techniques, fairly straightforward mathematical steps to put a number to this recorded signal. Before we get to that number, another common process that's used to bring some relevancy to the EMG signal is called normalization. And normalization is where we take that full wave rectified signal and we convert the data to some standard. And that standard allows us to compare between different muscles and different people. Each muscle in one person will generate a rather unique EMG signal, but by comparing the raw signal or the full wave rectified signal from one muscle to another muscle is tantamount to comparing apples to oranges. So that won't work. But if we can take the signal and if we can divide it by a standard contraction, a very common standard contraction is something called the MVC, the maximal voluntary contraction. So a person would be asked to contract their muscle as hard as they possibly can against external resistance, and the recorded EMG signal is considered to be 100%, and then we would ask that person to perform some functional task or a less than maximal contraction, and those data are converted to a value that is a percent of their maximal voluntary contraction. So as we see on this figure, we have time the label here isn't indicated, but we have time along the x-axis, and we have a percent MVC. So this could be a person lifting weights in the weight room of a particular muscle, and we see that at some point that muscle is generating an EMG signal at a single instant that's equivalent, that's equal to 100% of that muscle's maximal activation capability. But throughout the entirety of this contraction, what we see here is that the muscle is recruited to varying levels of its maximal capability, but still activated to a fairly intense level of activation between 50 and 75%. So that's just a subjective conclusion here just by eyeballing this, but as you might suspect, eyeballing it will give varyingly different results between people. So we need to have some sort of technique so that we can be much more objective in quantifying what's happening with the EMG signal. So there are three main, very commonly used measurement variables: the peak, the average, and the integral, which I'll explain here on this slide. So the units for the EMG is the unit is the millivolt. And of course, time is always going to be along our x-axis. And so what we have here is just a sample tracing of a full wave rectified signal. So all the negative values were flipped onto the positive values, and we have something that looks something like this. Now, this signal has all these peaks and valleys and all these jagged edges, and it makes it a little bit of a challenge to understand and where exactly we should take measurements from. So one common approach is to produce what's called sometimes referred to as a linear envelope, which is a mathematical process which just averages a series of points and replots them, and so it produces a much smoother signal. So this smoothing approach will now allow us to get away from these very sharp peaks and valleys, and gives us an opportunity to make a little bit more of a definitive indication of the level of activation of a particular muscle. One approach is to take the peak amplitude, and so when we talk about amplitude, that's the deviation along the y-axis. It's essentially how high the activity is. And so one way is to take the very highest value. Another approach that is commonly used is to take what's called an average amplitude. So on the red line here, the processed smooth signal, each data point is added up, divided by all the data points, the number of data points that were added up, and it yields an average value. Another very common approach is to take the area under the rectified signal or the area under the smooth signal, and that is referred to as the EMG or the integrated EMG. So taking the area under this curve, although this is beyond the scope of our discussion here, that is the mathematical definite integral of this tracing here. So I want to touch on one more mathematical or processing approach, and that's frequency domain analysis. And so we'll talk a little bit about the time domain here. So whenever we talk about domain always refers to what is on the x-axis. And so if we are examining the EMG signal in the time domain, time is going to be along our x-axis, and what we are evaluating is the amplitude of that signal over time. And so our units here are volts. Here we see a raw signal, and as we progress forward in time, we can use the techniques that were discussed on the previous slide. If we have an EMG signal expressed in what's called the frequency domain, frequency will be expressed along the x-axis, and so the amplitude of the signal will be plotted as a function of the inherent frequency of the signal. So if you refer back to the first slide of this recording, you'll see that each motor unit will generate muscle fiber action potentials with very unique frequencies to those action potentials. So if we take an expression of the inherent frequencies and plot them, it will generate this type of very characteristic shape, a very positively skewed distribution. And this mathematical process is called FFT, or a fast Fourier transformation. And this is a mathematical process where a complex signal is decomposed into its constituent signals that make up this raw signal and expresses those signals based upon their individual frequencies. And so there being a positively skewed distribution, we use basic statistics, measures of central tendency, to provide us with an indication of what this frequency profile will look like. The first one is called the mode, the most commonly occurring amplitude, or the frequency at which the most common amplitude exists. It's very rarely used in frequency domain EMG analysis. The most common and most valid approach is what's called the median frequency. So the median is also referred to as the center frequency, and it's defined as the frequency along the x-axis that divides the entire area under this curve in half, and it's the most commonly used one. Another commonly used, but to a lesser extent, is the mean frequency, the average frequency, which is skewed towards the tail here. Because the mean is influenced by these high frequency outliers, it will tend to skew in that direction. The median frequency, or the median statistic, is insensitive to outliers, which is why the characteristic frequency distribution of an EMG signal is conducive for using the median statistic rather than the mean statistic. And just as a reminder, the positively skewed nature of the frequency profile of a raw signal is inherent to the EMG signal. This is a very consistent pattern that appears in surface EMG signals. And so this is where we're going to end part 3 of our video. We'll start part 4 of our EMG module by beginning a discussion with the knee extensor muscle group, and this is the muscle group that we will use to illustrate a number of different examples in research studies.